Hello, fellow. My name is James Owusu-Appiah, and I believe in innovation and doing things differently. This video has been prepared for you to guide you through some well-known concepts that will aid your studies and preparations towards exam. Due to COVID, we cannot meet in person to discuss, so I hope this video finds you well and helps you achieve excellence. Thank you.
The approach now, you see, how we connect them will determine, the number of biases and all these things. That's where they come into play. How do we establish a relationship between these things so that they can be able to transfer data, right? We can be able to transfer data among them. So there are a lot of stuff that you can use, right? A lot of them, but the commonest and easiest one is the bias topology. So the bias topology is the commonest and easiest thing to use. And because this is your first and also doing this thing it's the best one to go with, at least. Because once you understand how the bias topology work, you will be able to kind of understand the rest, the other stuff. I mean, when the need arises. So with that out of the way, let's see. So how does the bias topology work? So with the bias topology, what happened is that you see we have a common bus where all the components that need data or that need to output data, they all share that one common bus. So they all read data from that common bus, and they all output data to that common bus. So that is it. That's how the bus topology work. The common bus topology. So with the so with that out of the way, let's see how do we so basically, yeah. So okay, let me just try and then start a bus. Okay, so this is our common bus. This is our common bus, just this line, and there we have it. Our common bus is ready. All right. Now, so there are two ways of implementing this common bus topology. So yeah, and the first approach is using a multiplexer and then demux, right? Yeah. So using a combination of these, you are able to create the common bus topology. And then, but there's another approach too, which is the use of trusted buffers, and that one seems to be much easier than easy to work with. So we will go with that one, the trusted buffers. And so later you'll see how that come into play. So basically, to do your connection, we are going to, for every component that we see, if any data, we just connect it to the common bus, right? And if we need to output data, then we also connect it output to the common bus. But for now, let's just look at the input, the input of all the components, right? So let's take this register for instance. By all means, it will need some input, data input, so we'll connect it to the bus, to the common bus. So let me connect it to the bus. And then this register too will also need data input, so I'll connect to the common bus. And so the program counter, yeah, so the load will also need to load value into it. Now what is the width of this bus? So okay, so this is a 8-bit bus, because as I said, we'll be designing a 8-bit microprocessor, so which means the data bus. So this common bus is what actually the data bus, right? And it's going to be 8-bit, yeah. So which means this wire here is a bundle of about 8 bits. As you can see, it's black, thick. So let me connect all the inputs here, and the same thing also go for these guys. Now for the current instruction register, this one is quite different, right? So we have to change the number of bits for this, and I'm going to use 4 bits. And why? And the reason for that is that, well, for now we don't have so many, so we don't plan about implementing more than 16 instructions. So because our number of instructions is going to be less than 16, so 4 bits seems fine for it. So that's why we're using a 4 bits for the current instruction register, right? And then for the micro instruction counter, right, this one normally is we are going to use 3 bits, right? So because now the choice of 3 bits is it just like on overall, I mean, our instruction will not require so many more than 8 steps to kind of execute. So that's just assumption for now, right? So we just assume that's how it's going to be like. Now for this feedback bit, actually, I will make it to be 3-bit, also 3-bit, and the reason for that later you will kind of see. Because this feedback bit, I'm just making it to be 3-bit. So you see, so which means we wouldn't be getting we wouldn't need so many other feedback from the system. So the 3-bit will be fine later when you're using it. So that's how we do. Now, if I attempt to connect these two registers together here, this register, try to connect this register to a line, you see it's turned this yellow or something, which means it's what, okay, incompatible with. So this is a 4-bit. This is a 4-bit register. You cannot connect it to a 8-bit input directly. So what we need is a wire splitter, and then so if you don't know how to use Logisim now, you can just go to the help and then you see the tutorial and the guide, and then you can see it's quite easy to work with. So you can just go through here and then you'll know how to use the software. So we'll need a wire splitter, and what we are going to do is that, so let me get one of them here, the wire splitter. I'm just going to try and split this input. So let me rearrange, then do some changes here to make it to be 8-bit. Okay, found out the 8th, and let me see what to do. First enter it and then the face soft. Okay, now with that, what I would want to do is that, so I can connect a wire splitter directly here. As you can see, so this one there's no problem. I can easily connect a wire splitter here. So what else I need to do is this. I probably want to make the output to be just one. I'm going to look for, okay. Alright, so I'm going to change the fan out. Yeah, so let me change that setting. Bitrate fan out. So let me be 2. Yep, so once it's 2, so which means this is the first 4 bits is this one, and then the lower other bit, and then other last 4 bits is this other side. So all I need is this 4 bits here. That's all I need. So I will just take them and connect all of it together. So I'll connect this one here because I need a data input. Okay, this is still not okay. This is 3-bit actually. So what I need to do is also further split it a little bit. So this is 3-bit, it's not compatible. So I'll just get another wire splitter to do that for me. You cannot split the output bit thing. So final will be 2. Okay, and the data bit is going to be 4 bits. Alright, and now I'll change the start of face east, then center that, and then okay, bit wait for 2 3. So what I want is I want the first these 0 here. So I'm going to change the setting a little bit. So this will also be up. You can see what is there, right? So the first 3 low order bits is what we'll take, and then just put it inside, send it here, and we can just tie the rest of the bits to ground. It won't do anything. We are not using those bits. So this is how you kind of establish a connection. So you can check out more on using Logisim. So I think basically we have connected the input of all the components that need what data, right? Now the output. Let's come to the output, right? So this RAM, this is the input address. So then whatever address location is here, that value, the values to other location will appear here at the data output. The same also apply for this. So now for this output, right? Let's see. If you see, the reason why we're able to connect all the inputs of these registers stuff, the reason we could connect all the inputs on our data bus, on this command bus without worrying about anything is because these the input impedance of these registers, or these or the logic gate as a whole, right? They have very high input impedance. Now, because of this high input impedance, what it means is that if we connect, if we have data on this data bus, right? We have data on this line, because these input have very high input impedance, it's very huge. These are in mega ohms. The input impedance is very high. So current here, so if whatever we have on this bus, it won't be, they won't affect anything that's on the bus, because current will not be able to flow through them, through them. So because of the high input impedance, current cannot flow through them. So as a result, connecting the input to the data bus is fine. But for the output of these registers, or the output of logic gates, they have low output impedance, and as a result, we cannot connect them directly on to the bus, right? Because if we connect them to the bus, then there will be conflict, you see. So let's say we connect the output of this to the bus directly, and also connect the output of this one also to the bus directly. So what will happen if these two are output data on the bus at the same time? There will be what, collision, and then the data will be lost, right? So as a result, we need some kind of control, so that we can only, so what we really want to do is that we need some kind of control, so that only one element can output to the bus at a time, not both. So, and what we will use is what we call the tri-state buffer, or the control buffer. Now let me search for that here. Okay, that buffer is here. Let me search for it. Okay, let me see. Okay, this is a buffer, right? So let me take this. No, not this one. The control buffer is not there. I'm looking for the control buffer. Okay, let me look for it. After that, I'll show you. Alright, so this is what I was looking for, the control buffer. This is it. So this is the buffer that we need, and why do we need it? Well, this buffer will do exactly what we want. You see, when this buffer is on, so let me connect it and then kind of explain how it works. I'll make the face the soft. Make the face, okay, good. Let it come. Alright, let me just leave it that way. Let's make it right. Alright, so this is our control buffer. Now let's see what this guy does. I'll try and explain what it does. Okay, the bit width does not match. Let me adjust the bit width. So this is 8-bit output, so I need an 8-bit control buffer, so I'm going to interface with it. So now it's fine. So what a buffer does is this, right? So when the buffer is off, now what do I mean by it being off? So let me just add this input to it and try to pass it onto it. So alright, so when the buffer is off, what happens is when this buffer is off, what it does is that it kind of it disconnects this line. It's almost as if when the buffer is off, it's almost as if you have disconnected this line. You have disconnected what is here from, okay, it's almost as if you have disconnected what is here from what is here. It's kind of disconnected, right? And basically what happens is that the buffer here, when it's off, it has a very high impedance. So if current is here, right, it can't go through, because the impedance seen from here to this side is very, very high. So as a result, when the buffer is off, nothing can be able to go through. So which means it's as if this now has a high output impedance. That's what will happen. Well, that's exactly what we wanted. So when the buffer is off, it will not, anything here cannot be seen here because of the high impedance of the buffer. So this buffer is called a tri-state buffer, right? So which means it has kind of 3 states: the normal, low and high state plus the high impedance state. Now, but when we turn on the buffer, so once you turn on this buffer, it just, anything I hear will pass it. So as you can see here, let me just write an FF inside the room so that you can see. So in that case, alright, let me see, it didn't appear, but I can write it right here. Okay, so whatever, but hope you get it. So basically how the buffer works, so whenever yeah, So it has very this high output impedance, right, when it's off, but when it's on, it will allow whatever that is added input to come to appear at its output. So if here's a high, you'll see a high. If here's a zero, you'll see a high. Zero when the buffer is on. Alright, so when the buffer is on, but when it's off, that is the case. So that's how we'll connect all the other components. On we'll connect all the other components. I mean, on onto the the bus, just using the same buffer. So let me get one of it. So that's how we implement our common bus topology. So with this, we can be able to connect all our components and not worry about data conflict. Okay. All right. We have all of these things, so we can just connect them on the bus.